On behalf of myself, Jim Forquin, and my co-authors, I'm happy to tell you today about our case for considering air-water CO2 exchanges in blue carbon accounting. So to date, blue carbon assessments have largely been based on measurements of organic carbon stocks and sediments. And this has been widely accepted by the community, and accounting mechanisms are now becoming a political reality. However, we all understand that the blue carbon burial is only one part of a really complex coastal cycle in habitats like seagrass meadows, where net carbon storage in sediments is complicated by a suite of additional CO2 release or uptake processes. In seagrasses, for example, organic carbon burial is complicated by factors like lateral mixing and a variety of benthic processes which will affect the overlying water carbonate chemistry and thereby can affect air-water CO2 exchange. This can include features like calcium carbonate precipitation, as well as these benthic biogeochemical processes that produce alkalinity, like denitrification and sulfate reduction. And all these processes cumulatively will have an impact on CO2 exchange with the atmosphere. But on a global scale, how important is this air-water CO2 exchange, and how does it compare with rates of potential blue carbon storage? To address this question, we put together the first ever meta-analysis of air-water CO2 fluxes in seagrass meadows using direct measurements by atmospheric eddy covariance. So as you might expect for coastal waters, we saw that CO2 exchange was highly variable at each of our 6 sites, with all seagrass meadows at times behaving as sources or at other times as sinks for CO2. And all were varying between source and sink behavior over hourly, daily, seasonal, and synoptic timescales. While I don't have time to discuss all of the drivers, tidal forcing appears to play a dominant role in shaping global trends in CO2 flux. This can be due to a complex interaction between lateral carbon exchanges, bottom-driven turbulence, and pore water pumping. We observed and show here in this figure that sites with a larger tidal range had greater CO2 uptake, suggesting the exchange of water of high or low CO2 concentration between and across adjacent ecosystems. When we place these CO2 fluxes into the same units as carbon burial rates, we see that CO2 fluxes were as large or larger in magnitude compared with these literature carbon burial rates. And for this reason, we argue that air-water CO2 fluxes can act to counteract or enhance net blue carbon storage by pushing the net ecosystem exchange of carbon in either a positive or negative direction. But how do we explain the extreme global variability in both the magnitude and direction of CO2 exchange? Well, this is a very complicated question that requires detailed studies at each of these individual sites, which involve comprehensive carbon budgeting. So to this point, we conducted a detailed study in a subtropical seagrass meadow in central Florida Bay. This is a really interesting site because not only is tidal mixing quite limited, meaning that what happens here stays here, but it's also one where calcium carbonate is produced. And the production of calcium carbonate generates CO2, which could potentially offset some blue carbon storage. However, prior global meta-analyses such as these have argued that much of the carbonate that's buried in these systems is either A, imported from adjacent ecosystems, or B, is simply redissolved in sediments. And as a result, have argued that perhaps only 30% of net blue carbon burial might be offset by net ecosystem calcification. So this is an assumption that we wanted to test in a study that I will summarize now. So in this study, we directly measured both air water and sediment water fluxes in conjunction with pore water geochemical sampling to constrain biogeochemical processes such as denitrification, carbonate dissolution, and sulfate reduction. And these benthic processes are important because they can drive sediment water fluxes of total alkalinity and thereby control net air-water CO2 exchanges. This is the first time that such a robust carbon budget has been compiled for a seagrass meadow, which includes direct eddy covariance measurements of air-water CO2 exchange, as well as benthic pelagic exchanges. So, while prior studies have shown this seagrass meadow to be net autotrophic with respect to oxygen, we observed small but consistent net CO2 release to the atmosphere. These CO2 emissions were greatest during the warm summer months, and especially in the late afternoon, which may be counterintuitive because this is when seagrasses are most productive. But what causes a site to be a net CO2 source to the atmosphere? We answer this question by digging into the benthic biogeochemical processes that act to drive net CO2 exchanges with the water column. So first, we know the site to be a net producer and accumulator of calcium carbonate because it's isolated from other calcifying ecosystems nearby, like coral reefs. Yet, the carbonate content is greater than 90%. However, the CO2 produced by this net calcium carbonate precipitation can be offset if these carbonate minerals are simply redissolved in the sediments. To this point, we do see excess pore water dissolved inorganic carbon, suggesting that calcium carbonate dissolution does occur, and the oxygen isotopic evidence on sulfate indicates that this dissolution is likely sustained by the reoxidation of sulfide diffusing up from downwards. And this is consistent with prior work 20 years ago by Ku et al. However, pore water DIC isotopes were very enriched in delta 13C, and our mixing model presented here indicates that this is likely driven by the consumption of isotopically light DIC by carbonate reprecipitation. And again, this is consistent with decades of prior work by researchers far smarter than myself, describing coupled dissolution reprecipitation of carbonate minerals in sediments like these. And this recrystallization of calcium carbonate is a bit of a fly in the blue carbon ointment, so to speak, because it enables the net preservation of carbonate minerals that were produced in situ, thereby supporting net CO2 emissions from the ecosystem that we directly measured with eddy covariance. An additional potential CO2 sink in seagrass sediments is total alkalinity production via denitrification. However, while we do see denitrification hotspots at this site, for example at high-density seagrass meadows, our direct measurements indicate that this seagrass meadow overall is net nitrogen fixing, meaning that denitrification does not counteract the CO2 emissions produced by calcification. And this is in line with, again, prior work in low-nutrient oligotrophic tropical estuaries, which are often net nitrogen fixing. So when we put all of these processes together into a comprehensive carbon budget, we see that this system is by far dominated by net ecosystem calcification, which can explain about 95% of the directly measured CO2 emissions. Organic carbon burial, which is that purple bar, can act to offset about 5% of these emissions, while net sulfate reduction and iron reduction only reverse about 1% of the calcification-driven CO2 emissions. And finally, by playing with the budget terms, we find that we would need to increase organic carbon burial by an unrealistic factor of about 20 for the site to become a net CO2 sink. Likewise, in the figure on the right, we would need to use, for example, massive iron fertilization or pyrite burial, which could, in theory, push the site back towards net carbon sequestration, although we don't suggest this as a management approach. Lastly, if you're interested in more details in this study, please stay tuned for our related publication, which should be out in the next issue of Science Advances. So to summarize, in this study, we observed net CO2 emissions from our tropical seagrass meadow, and we attribute this specifically to the net precipitation and burial of calcium carbonate minerals being greater than the burial of organic carbon. This is especially important given the broad distribution of blue carbon sites in the tropics, where calcification is greatest, and especially this is an area where studies are limited due to the known bias in the literature in favor of temperate as opposed to tropical seagrass systems. We argue that blue carbon assessments that don't consider air-water CO2 exchange have the potential to severely over or underestimate net carbon sequestration potential, and this could be a problem as blue carbon offset schemes are rapidly becoming a political reality. And most importantly, I have to say a huge thanks to the colleagues, as both of these studies discussed here came out of totally unfunded projects and were really a labor of love for all of us. Our work would have been absolutely impossible without the generous partnerships from all involved, and it has been an absolute joy to work with this amazing group of interdisciplinary scientists. So thanks also to you for listening, and for the Blue Carbon Working Group for inviting me to this session. With that, I'm happy to take questions now, or over email, Twitter, or whatever else later. Thanks.